So now seventh property of vectors. Now in seventh one we have for each real numbers, for each real number, sorry, A, and each pair of vectors x and y. There is A of x plus y. A multiplied with ax plus y is same as ax plus ay. So if we operate scalar on some addition of two vectors, then it is given by this. So these two are same. Now eighth one, last one. For each pair of real numbers A and B, and each vector x, this A plus B into x, that is same as, now we are taken as scalar addition of two scalars and multiplication with one vector. This is same as ax plus bx. So these two are the distributive properties, scalar over vector, and here two scalars and one vector. So these are the properties, 8 properties which a vector must satisfy. So now we can start with our main topic, that is vector spaces, because it deals with vectors only. Now vector spaces. So first of all, the definition, then we can give some examples. A vector space. So a vector space V, this is the notation, over a field from which we can take scalars only. V contains vectors and F contains scalars. Over a field F consists of a set on which two operations are defined. Two operations are defined so that for each pair of elements x, y in V, x, y are vectors, x, y in V, and for each element, now we have to pick scalar, for each element A in F field and each element x in V, there is a unique element ax in V and x plus y in V. So what we have, a vector space V over a field F consists of a set with two operations, like if we have this V plus and multiplication, this is a vector space over F, or you can write it as V over F. So what we have to take, for each pair of elements x, y in V and for each element A in F, there are two elements in V, like for each x there is a unique element ax in V, and for each x and y there is a element x plus y in V. So if we can write this, if x and y belongs to V, there are two vectors in V, this implies what? X plus y also belongs to V. This is the closure property with respect to addition, with respect to first operation, this one. Now second one, if A is a scalar belongs to F and X is a vector belongs to V, this implies what? The AX belongs to V. This is the closure property with respect to scalar multiplication. So this happens internally. Two elements belongs to V and their addition also belongs to V. And this is externally. One element belongs to field, one element belongs to vector space, and the multiplication belongs to V. So these two are the properties, the standard one. So if there is any set with two operations satisfies these two and such that the following conditions hold. Following conditions hold. Then only we can say that V is a vector space. So what are those conditions? First axiom is for all x and y belongs to V, x plus y is same as y plus x. This is commutativity of addition, as I discussed before. Now second one, for all x, y, z belongs to V, x plus y plus z is equal to x plus y plus z. This is associativity of addition. All the 8 properties are same as the properties which satisfied by vectors only. So this one, additive identity, x plus 0 is x. Now fourth one is, this is x plus y is 0. So this is, you can write additive identity. And this is additive inverse. Inverse with respect to addition. Now fifth one is multiplicative identity. This is multiplicative identity. Now sixth one is scalar multiplication, associativity with respect to multiplication. This is given as A of bx. Now seventh one, distributive, scalar over vectors. This is ax plus ay. Now this is distributive. Now last one, this distributive property over scalar addition. So this is ax plus bx. This is also distributive property. And this is associativity with respect to scalars. So these are the properties which we have to satisfy for a vector space. Now this x plus y is called sum of x and y, and ax is called product of a and x. So as you know that these a are scalars, a are called scalars, and x, y, z, these are called vectors. These belongs to f and these are belongs to v. So I just want to explain one more thing. If you have this type of component like a1, a2 and so on, an, this belongs to f scalar, this belongs to f, this belongs to f, and the whole element belongs to what? Fn. So this type of element we call it as n-tuple, and these AIs are called entries and component. You can say that it is components. So if we have two type of n tuple vector, like if you have a1, a2, an, and you have b1, b2, so on bn, these two scalars belongs to fn, and these two are equal. These two are equal if and only if the entries are equal, like a1 is b1, a2 is b2, and so on, an is bn. And this is same for vectors also. If you have like this, you have two elements x1, x2, this is equal to y1, y2, and these are vectors, xi's and yi's are vectors. So the components are also equal. X1 is same as y1, x2 is same as y2. So if this is two tuple or two length vector, you can say that. So these two are same if and only if the entries are same. Now there is a term row vector. Row vector means if you have this type of notation, a1, a2, an, like this. Suppose AIs are vectors. AIs are vectors. So this is a row vector. And a matrix consists of vectors is given by, these are just notations because these are helpful for next coming examples or next some proofs. So I'm just giving you the notation. Now matrix which consists of field elements. Matrix consists of field F elements. This is given as A11, like if you have n cross n matrix, then A12, and this is A1n. Now second row is A22, A2n. Last one AN1, AN2, ANN. So this is your n cross n matrix which consists of scalar entries. Similarly, we can obtain a matrix for vectors also. So now there is a zero matrix. Zero matrix means all the entries are 0. And diagonal matrix means this A11, A22, and remaining entries are 0. The only diagonal entries are non-zero, otherwise all remaining entries are 0. So this is just the definition of vector space.